So everything we've talked about so far in chapter 4, we did balancing equations, then we started stoichiometry. And the two questions we did as examples, we only had one starting material. Like when we were doing this octane with oxygen example, we were looking at the amount of CO2 that would be produced from that 225 grams of octane. Since there was no mention of oxygen anywhere in the question, we're just going to assume that that was excess. And that the reaction would just stop and be done based on that mass of propane of 225. So if we were looking at oxygen, we'd still have oxygen at the end. Like after the reaction was done, there would still be oxygen present, but the octane would be gone. So that's why the reaction would come to a stop. That's not always the case where the second reactant is just assumed or listed as excess. And if that's not the case, it's called a limiting reactant problem. So if you remember these from intro chem, it means you have more work to do. So what'll happen now is you'll be given a balanced equation, unless it's one where you can get it yourself, and it'll ask you about the mass of product or the molecules of product, but you'll be given quantities of both reactants. And the problem is that you won't at first glance be able to figure out which one is limiting. You're going to have to do some work to figure that out. Though there's two different ways to do these. The way that I thought made the most sense to me, and I thought it felt like it was the shortest pathway, you may disagree with that, is to take the first reactant, figure out how much product it could make. Then take the second reactant, figure out how much product it could make, right? But there are two ways of doing this, and I know different teachers do it differently, and you may disagree. You may say, you know what, I like the other way better. So I'm going to show you both, and then you pick which one you like better. Okay, so limiting reactant, right? Now what'll happen is you'll have quantities of two reactants, and one of those is going to run out first, but we don't know which one. So we have a little bit more work to do. And you're always then asked about how much product, right? So you have to figure out which one of the two reactants runs out first. Then that one predicts how much product could be made. Now, when we do these calculations using perfect molar masses and perfect mole ratios and perfect constants like Avogadro's number, those numbers that we get based on the stoichiometry, these are called theoretical yields, right? In theory, if everything's perfect, that's what we should get. But we know that when we go into lab, what we actually get is not always what we think we should get. And that's called the actual yield. So when I go to find the percent yield for a reaction, it's almost like a grade. How well did we do? We're going to take the actual yield. And because we're not in lab, this is going to be given to us for the lecture class because it's not like we're doing these reactions for lab. But the theoretical is based on our stoichiometry calculations. So we've got this reaction here of iron 2 sulfide reacting with hydrochloric acid, which will produce iron 2 chloride and dihydrogen sulfide gas, really hydrosulfuric acid if it's in solution. Slight distinction, but don't worry about that. If I gave this to you on nomenclature, you would say hydrosulfuric acid, binary acid. Okay, so this question says we've got 10.2 grams of HCl added to 13.2 grams of FeS, iron 2 sulfide. And we want to know how many grams of H2S could we make. So that is the classic limiting reactant problem, right? The question mark is still the B. It's still where we're headed. And the quantities of both reactants, these are both A's. So I'm going to call them A1 and A2. All right. So I'm going to show you the way I like to do these. And then on the next example, I'm going to show you the other way. And then you pick which way you like better. And then I'm going to just stick with my way from here on out. It's not my way, the way I do it. Just because that's the one I think is the simpler pathway. But I want you to be able to know how to do both. Well, I'll explain that in just a second. Okay, so FeS and HCl, we have quantities of both of these. Now the reaction's going to go and go and go until one of those two reactants runs out. And it would be great if we could just assume that the one that's in less mass is the one that's going to run out first, and that's not true. Because really this comes down to moles, right? And for every 1 mole of iron 2 sulfide, I need 2 moles of HCl. So right there I can see I need twice the number of moles of HCl as I do FeS. The other problem is that mass in order to get to moles, it's based on molar mass, and these two substances have a different molar mass. So it's not as easy as just looking at the two values given and picking the limiting reactant. We definitely have more work to do. So as I've been doing with the last two examples, I want to think about the conversion factors. What do I need here? All right, well, since I have mass for all three, right? Iron 2 sulfide, HCl, and then I'm looking for mass of H2L to H2S. I need molar mass values for all of those. Okay, so molar mass. All right, first, the FES. I'm going to take 55.85 for iron, 32.07 for sulfur, and I get 87.92 grams. For the HCl, remember, just one of those, 35.45 plus 1.01, so 36.46. And then for the H2S, I've got 32.07 plus the 2.02 for the two hydrogens, and I get 34.09. All right, so those are the molar mass values for each of those. So 1 mole is 87.92 grams for FES, 36.46 grams for HCl. Now in this one, this question, there's no mention of molecules or atoms, so we're not going to need Avogadro's number here. We're just going to need molar mass values. So the way that I always thought this was the easier way to do it, for a limiting reactant problem, I take my first A1, the 13.2 grams of iron 2 sulfide, and I figure out how much H2S that could make. The problem is that that calculation assumes that, you know, the sulfur's coming from the iron 2 sulfide, but the hydrogen comes from the other reactant. So this calculation assumes that I have plenty of HCl. And that's not true. I don't have plenty, but it's an assumption that'll work if I do a second setup. So the second setup is that I take my A2 and I now convert that to B. So you're going to have twice the work, two calculations to do rather than just one. And at the end, what you're going to do is you're going to circle the smaller. So just throwing out some easy numbers. Let's say the 13.2 grams of FES could make 100 grams of H2S, but the HCl could only make 50. Well, then I can only make 50. I don't have enough to make 100. So that's why you circle the smaller at the end. Okay, so let's do the first part. Let's take A1, convert to B. All right, remember to always, always, always go to the same unknown at the end. We always go to the same endpoint. All right, so I'm going to take my 13.2 grams of FES, right? That's my A1. I'm going to always go to moles first. So I need to get rid of grams of FES. We're going to go to moles of FES. Molar mass, 1 mole of it, 87.92. Those are the numbers I had for you up here from the periodic table. Now, this is where sometimes students go a little sideways. We know we're getting rid of moles of FES here. When you read the question, you might be tempted to convert to HCl, but we always want to go to the unknown. And that's what we're looking for, the grams of H2S. So on top, we want to go to moles of H2S. All right, mole ratio is where we bring in the coefficients from the balanced equation. In this case, it's 1 to 1. All right, so we just put 1 to 1. All right, one more setup here. For 1 mole of H2S, we're going to make 34.09 grams because that's the molar mass. All right, so 13.2 divided by 87.92 times 34.09, I get 5.12 grams of H2S. All right, now remember that sulfur is coming from the FES, but the hydrogen's coming from the other reactant, and that's not part of this calculation. So I don't really know for sure if that's right. So now I have to take my A2 and convert that to B. So I start with my 10.2 grams of HCl. 1 mole of HCl is 36.46 grams based on the periodic table. From the balanced equation, for every 2 moles of HCl, I make 1 mole of H2S. All right, and then 34.09 grams of H2S for every 1 mole of H2S. So this is why I felt like it was simpler. And I'll show you, like, you have to go to moles for both starting quantities anyway. And when you do the two setups, you take A1 to B, you take A2 to B. Let me go ahead and get this answer. 10.2 divided by 36.46 divided by 2 times 34.09. I get 4.77 grams of H2S. All right, so when I look at this, I'm going to the same endpoint, right? So the last thing I write down here, it's the same for both because we're going to the same place. So always remember that when you're doing a limiting reactant problem, always go to the same endpoint. And what I'm done at this point, I just have to indicate which is the answer. So the 13.2 grams of FES could make a little over 5 grams of H2S. The 10.2 grams of HCl, it can't get there. It doesn't have quite enough to make it happen. It can only get to 4.77. So what I do is I circle the smaller. The 4.77 grams is the most I can make because at that point, all of the HCl reactant is gone. It's been used up. So that is the most H2S I can make. So this calculation tells me sort of everything I need to know. It tells me that 4.77 grams of H2S is the max theoretical, right? Again, where this is in theory, max theoretical yield. And that is because the HCl is the limiting reactant. So we did calculations like this in Intro Chem. We're going to complicate it just slightly, I think on the next page, because what we figured out by the calculation is the reactant that runs out first limits how far the reaction can go, which means that the HCl here is the limiting reactant. But what that also means then is that at the end of the experiment or the reaction, you would have some FES still unused and left over. So it's called the excess reactant. You have extra of it at the end. But the way I thought this was easiest to do, made it more straightforward, is in a limiting reactant problem, take your first reactant, figure out how much product it could make, start over. Now the second reactant, figure out how much product it could make. You're going to the same endpoint. So the same conversion for both on that last, conversion number 3, right? Same molar mass, same substance. Circle the smaller, right? Your answer, the smaller answer is the max yield, theoretically, because it shows you that that reactant that gave you that number is the limiting reactant. So that's the way I like to do it. Here's the other way you can do it. We're going to go to the next example. So for this one, we want to know the percent yield if 19.2 grams of ipentyl acetate was made from reacting 25 grams of ipentanol. So I'll put the 25.0 grams under ipentanol with 25 grams of the acetic acid. All right, and then we're given this second part, which is we have 19.2 grams of ipentyl acetate. But what's different here is we're looking for percent yield. So let's kind of break this up. This is sort of 2 parts. If we're finding percent yield, the formula is we need the actual yield over the theoretical times 100. All right, and like we talked about, the theoretical comes from our calculations. The actual has to come in the question because we're not in lab. We don't have data. We're given the data. So when you look at all these numbers, sometimes students will say, well, how do I know what do I use for the actual yield of those 3 numbers? And what I think makes total sense is that since we're looking at a percent yield, it's always going to be for a product, right? Yield means product, produce, right? So we are looking for the percent yield of the ipentyl acetate. That's what we're looking for. And that means that the actual yield of that ipentyl acetate must be given. And that's the 19.2 grams. So that 19.2 grams, we kind of just set that on the table and forget about it because we're going to use that at the end to do the percent yield calculation. So what I need first is to find the theoretical yield of the ipentyl acetate. So first thing I'm going to do is let's find the theoretical yield of the ipentyl acetate. So I'll just stick with my abbreviation, the IPA. All right. Okay, so we could do it the way we did in the last example. take your A1 acetic acid, convert to I-pentyl acetate. Start over, take your I-pentanol, convert to the I-pentyl acetate. The alternative way of doing this is you still start with both of your reactants. So we got the 25.0 grams of the acetic acid, HAC, and we have 25 grams of the I-pentanol, which was abbreviated as IPOH. We still have to do what we did before. You always go to moles first, no matter what we do. All right, and the molar masses are given to us right here, so we don't have to go look for them. Acetic acid is 60.06 grams per mole, and the I-pentanol is 88.17 grams per mole. All right, now the part that you don't want to omit is the mole relationship. And this is where, to me, it gets a little wonky, but it still works. So when we do it this way, which is the second way, the first thing we're doing is, and I'm going to call this part A, is just to figure out which one is the limiting reactant. All right. So it breaks, when you go to find a theoretical yield, it kind of breaks it up into two parts. Now, we did two parts up here. We took A1 to B, A2 to B, circle the smaller. What we're going to do here is to find the theoretical yield, we're going to figure out which one runs out first. So we have the 25 grams of both reactants. We divide by the molar mass to get to moles. What we don't want to forget is we want to know how many moles of that reactant do you have per reaction cycle. And I'm going to explain that here in just a second. All right, so when you go to do some of the quiz questions, it'll ask you on some of the questions just to find out which one's limiting. It doesn't ask you about the product. It's just going to say which one is the limiting reactant. This is what you would do if all you're trying to do is find out the limiting reactant. Now, technically, if you want to find the limiting reactant and it doesn't specify what product to use, you can pick a product and find out the limiting reactant that way. You can do that because it's just math. But if all you want to do is find the limiting reactant, what you have to do is start with the mass of each reactant, divide by the molar mass of each of those to go to moles. And then don't forget to look at the coefficients in the balanced equation. Now, in this case, it's 1 to 1, but that's what we want to make sure and capture here. So cycle isn't really a unit. So I kind of put that in parentheses because that's not really a unit. Like grams is a unit, moles is a unit. But I have to put something there because it's the only thing that makes sense to me. For one reaction cycle, I use 1 mole of acetic acid. So basically those coefficients that we've been focusing on for this chapter for stoichiometry, again, that's where it's coming in. Nothing in front, so it's an implied 1, right? So 1 mole of acetic acid for every time that reaction goes through a cycle. For the I-pentanol, also 1, right? 1 mole of I-pentanol for every cycle. If this had been a 2 to 1 ratio or something like we had up here, that would have been an important step because we need twice the moles of HCl as we do FES. So you got to make sure and factor in that coefficient. So mass to moles first, makes sense. That's what we're used to. Divide by that coefficient to make sure we capture if there is a mole difference. So 25 divided by 60.06 means I have 0.416. And again, there's no unit here, which is the other reason I think I didn't like this. 0.416 cycles from the vinegar, the acetic acid. Then for the I-pentanol, when I do the 25 divided by 88.17, I get 0.284 cycles. All right, so again, no unit on that. All right, so if this were on a test question, you just leave off the unit. All right, but at this point, what I understand, and this is all I understand at this point, is that because this is the smaller number at 0.284, that tells me that the I-pentanol is the limiting reactant. The acetic acid could keep going, but the I-pentanol is going to stop. It runs out first. So if all we're trying to do is find the limiting reactant, so just trying to find limiting reactant, go to moles first. Okay, so first go to moles. And then second, make sure you divide by the coefficient in front. Or I'll just abbreviate that, divide by the coefficient. So that's what I highlighted. Now we're not done. That's part A. Now we got to do part B. Now we find the mass of B. All right, so now we can go ahead and convert to product. What we now know is acetic acid excess, ipentanol is where we're limited. So we're going to start again with that 25 grams of ipentanol. 1 mole, 88.17 grams. Mole ratio, getting rid of the ipentanol, going to the product, which is the IPA, the ipentyl acetate. In our balanced equation, it's all just a 1-to-1-to-1 ratio. So that's where those coefficients are coming in, right? Always in that mole ratio step. And then the last thing here is we want grams. We know we want grams because the actual yield was given in grams. So we need the theoretical to also be grams. So 1 mole of the IPA, molar mass was given to us up here, 130.21. So I just went ahead and grabbed all those to make it a little bit shorter. So 25 grams divided by 88.17, and then multiply that by 130.21, and you get 36.9 grams of the ipentyl acetate. Now, again, based on molar masses, these are perfect numbers. This is the theoretical yield, right? In theory, that's how much IPA we should have been able to get based on our limiting reactant of the IPOH or the ipentanol. Now, after all that, we're not done. Now we go back and we say, okay, what is our percent yield? Percent yield, the actual was given at 19.2. We just figured out a theoretical of 36.9. Then we can find our percent yield. So we expected 36.9, but we only got 19.2. So that means we had a 52.0% yield. Okay, so a couple of things to take away from this. Number one, if you're ever asked for the percent yield, it will always be for a product, right? So something on the product side. So when you're given all of these values and maybe you're not really sure what you're looking for, of these three, it's going to be the product. So acetic acid and ipentanol are reactants. A yield, right, means produced. So we knew that we were looking for the percent yield of the ipentyl acetate. That's number one. Number two, if we are looking for the percent yield, actual has to be given. So this 19.2 grams of IPA, that has to be the actual yield. And it does say it. It says that was made, right? So that's our actual yield. We pull that out because we're going to save that for later when we do the percent yield calculation. Now, this also tells me that this is my B. This is what I'm looking for, because if I knew how much I actually got, I need to then calculate what should I have got. So to find the theoretical yield, when you have a limiting reactant problem, you could definitely do this the way we did the previous example. 25 grams of acetic acid, convert to mass of ipentyl acetate. 25 grams of ipentanol, convert it to mass of acetic acetate, circle the smaller. This is the other way, though, of doing a limiting reactant problem. You start with the mass of each of those two reactants, divide by the molar mass to get to moles, and then make sure and divide by the coefficient from the balanced equation. Again, what's weird here is this isn't really a unit. Like, you just basically are putting 1 in the numerator, which a lot of students don't like, and I don't blame you. I didn't like it either. But at this point, this tells us that the ipentanol will run out first because it just can't go as far. So now I know, since that's my limiting reactant, that's the A I want to start with to figure out my B. So I start with my mass of limiting reactant, convert that to my mass of product, theoretical yield, because it's based on perfect values, right? Then I can go back and calculate my percent yield. Actual given in the question, theoretical based on calculation, times 100 and keeping 3 sig bigs, because that's what all my measurements had. All right, so to me, this seemed like a more, it's not complicated. It just seemed like it was more, I don't know, more indirect, maybe. I felt like this other way was just more direct. Go A to B, start over, A to B, circle the smaller, done. This is a little bit more like, well, let's just go like halfway, figure out how we did, and let's go back to the beginning and then go all the way. I don't know. It just seemed like it was more work. Like at this step, you have basically your mole to mole ratio just about. So you just need one more conversion factor on each of these setups. And remember, it's the same for both. It's like so you got to figure it out anyway. I don't know. That I like option one. This is option two, but you use whatever you're looking for, whichever one you like better. And that depends probably on what teacher you had for intro. And also, if there is a question where it's just asking you for limiting reactant, doesn't ask you for the B. If it's just asking you for limiting, then this is what would get you there. All right, so mass divided by molar mass to go to moles, and then don't forget to divide by that coefficient. Okay, so if you're only asked for limiting reactant, that's your step, your pathway. All right, so next question. Okay, so remember how I mentioned we can complicate this a little bit from what we did in intro. We've got a balanced equation here of nitrogen dioxide with water to make nitric acid and nitrogen monoxide. And it says that we've got 5 moles of NO2 reacting with 1 mole of water. They react completely until something runs out. How many moles of the excess reactant are present? Okay, so in this question, we're not asked about HNO3. We're not asked about NO. It's not percent yield. So this is a little bit different, right? So if I think about it too, there's no mass values here. So we don't need molar mass values. There's not particles. It's not atoms or molecules. So we don't need Avogadros. So here's what we're doing here. We're really just figuring out which one's limiting and which one's excess. So we have 5 moles of NO2. That's reactant A1. We have 1 mole of water. Now, if I go back to our last example, I had said, okay, when you're trying to find the limiting reactant, go to moles first. Well, we already have moles, so we saved a step. The only thing we have to really evaluate here is the coefficient. So for every one, again, reaction cycle, not really a unit, we use 3 moles of NO2. For water, every time we go through one reaction cycle, we use 1 mole of H2O. And again, the 3 and the 1 are just coming from the balanced equation, the coefficients in front. All right, the 1 mole and the 5 mole, that's coming from the actual question. Those are the measurements. So if I look at the first substance, the NO2, you get 1.667, right? So I'll just put 1.6 repeating. And then for the water, you just get a 1. So what we can tell then is the water would be the limiting reactant. The NO2 would be excess, right? We're going to have extra of that left over. Question is, how many moles of the excess would we have left? So now that we know water is the limiting reactant, we're going to start with our quantity of water, right? In this question, we were told that we had 1 mole of water reacting with 5 moles of O2, but we know some of those moles of, NO2 are not going to be used. So we have our 1 mole of water that we were given. I'm going to look at the mole to mole ratio. For every 1 mole of water, we need 3 moles of NO2. So what that tells me is, and I think you can see this just by looking at the equation, that if I have 1 mole of water in this reaction, I'm only going to use 3 moles of NO2. It's a 1-to-3 ratio. Well, we had 5. So how much is excess? So the last step here is we had 5 moles of NO2 total. All right, and it froze. It'll come back in just a second. So we had 5 moles of NO2 given to us again in the question. And we used 3. There we go. So I'm going to subtract the 3 moles of NO2 that we used. So how much do we have left? We have 2 moles of NO2 that are going to be present in excess. All right, so this particular question may not look quite so bad because it's just moles. So the math here wasn't that bad. But imagine if instead of moles, it gave us grams. So let's say we had 5 grams of NO2 and 1 gram of water. Well, then we got to go to moles first using molar mass. But then it's all the same. Figure out which one's limiting first. Once you identify the limiting reactant, right? In this case, we found out that the limiting reactant was the water. Then we start with that amount of water given to us in the question. Go figure out the amount of that second reactant, the excess reactant that we actually used, and then subtract that from what was given. So we were given 5 moles of NO2. We only used 3. So that means we had 2 moles of NO2 left over. It would be the exact same process if you had mass. It just would be slightly more work only because you got to do the molar mass values and such. All right. Okay, so stoichiometry, kind of tabling that for a little bit. Now what we're going to do is look at different types of reactions. So we've got a few equation types that we're going to learn in this chapter, and then a few equation types that we're going to learn in chapter 5, which is after the first test. So chapter 4 is where we stop for the first exam. That means that after today, Tuesday is going to be review, and your test already is coming up Thursday next week. We move so quickly over the summer. So combustion reactions, I think these are like the easiest of the types. What we have in a combustion reaction is we have some kind of hydrocarbon, right? Hydrogen and carbon. Hydrogen is second because it's not an acid, so it's not written first, it's written second. So we've got our hydrocarbon. We react it with O2 from the air. That's our fuel for fire. All the carbon comes out as CO2. All the hydrogen comes out as H2O. Now the water's in the gas phase because we're burning, right? It's hot. So the water's it's past the boiling point. Oxygen gas from the air, and then the hydrocarbon, it depends. The bigger it is, the heavier it is, it will go to a liquid, sometimes a solid. If it's a relatively small hydrocarbon like natural gas, CH4, it'll be a gas. So the state depends. That'll be given to you. So C5H12, we've got pentane reacting with O2. This is what you look for, right? We know we see the hydrocarbon with oxygen. So you're always going to give me the same 2 products. It's always going to be CO2 and H2O. All right. In a perfect world with combustion, when it's efficient, these are always your 2 products. So we're going to put always CO2 and H2O on the product side. All we have to do is balance. Okay, now oxygen we're going to save for the end because like we talked about earlier, it splits. It goes from 1 spot to 2 spots on the product side. So let's start with carbon. We've got 5 carbons in the pentane. All of that carbon goes to CO2, right? And so that subscript on the carbon literally goes right in front of CO2. 5 carbons, 5 carbons. So we put a 5 in front of CO2. For the hydrogen, we have 12 hydrogens in the hydrocarbon. On the product side, we need the multiple of 2 to get us to 12 because H2O has 2 hydrogens per molecule or mole. So to get to 12 total to match the reactant side, I need to put a 6 in front of water. So there's my 12 hydrogens. Last thing I do then is now the product side I assume is done. I'm going to total up my oxygens on the product side. So in the CO2, I have a coefficient of 5 and a subscript of 2 for the oxygen. So I got a total of 10. For the water, I have a coefficient of 6 and a subscript of 1. So 6 times 1 is 6. So 6 oxygens in the water plus another 10 oxygens in the CO2 means I have a total of 16. So on the reactant side, to get a total of 16, I need to put an 8 in front of O2. And that is our balanced combustion equation. Nice and simple. Next one, we've got C10H22, all right, decane, reacting with O2. Same 2 products. We're going to put CO2, gas phase, and H2O, gas phase. Again, whatever that subscript is on the carbon in the hydrocarbon goes right in front of CO2. So 10 carbons means we put a 10 in front of CO2. For the hydrogen, we've got 22 in the hydrocarbon. So that means we're going to put an 11 in front of the water because 11 times 2 is 22. Whenever you end up with an odd number in front of the water, you're going to end up with an odd number of oxygens. And so that's okay, but I'll show you what's going to happen. So when I go to total up my oxygens, I have 10 CO2s times the subscript of 2. So I've got 20 oxygens here. Then with the water, I have a coefficient of 11 times the subscript of 1. So 11 oxygens here. So 20 plus 11 means I have 31 total oxygens. So on the reactant side, I need the multiple of 2 that gets me to 31. Okay, you have some options. You can do 15.5. That works fine. You can do 31 divided by 2. That works fine, because if you think 31 divided by 2 times 2, the 2's technically cancel out, so there's your 31. However, you can't write it as 31O, right? You can't like take off the subscript of 2, because going back to something we talked about earlier, oxygen, it has to be O2, right? Oxygen gas, you can't just say O. So it has to be O2, which means this has to be 31 divided by 2. All right, so if I now think of it, 31 divided by 2 times 2, it's still 31, but there's my 31 oxygens. Now, textbooks, they sometimes don't like the fractions. And so if you look this up in the answer key, to get whole numbers, all we would do here is multiply everything through by 2. So instead of 1 decane, we would put a 2 in front of C10H22. Instead of 31 divided by 2, we'd have 31 in front of the O2. Instead of 10 CO2s, we'd have 20. And instead of 11, we would have 22 in front of the water. It's the exact same equation. It's just one has a fraction and the other one doesn't. You pick whichever one you like. I'm just saying if you'd gotten the decane question on the homework and then you went, not my answer key, but you looked at the book answer key, it's going to give you the one that has whole numbers in it. I allow fractions. I think fractions are fine. Now, the only exception would be is if the question says, what is the, let's say it gives you this decane plus oxygen, and it says, okay, how many moles of CO2 would be made in the balanced equation, assuming only a whole number ratio? Like if you see something like that, where you have to have everything in a whole number ratio. But honestly, it really doesn't matter, because if we're doing stoichiometry with this, like we did at the beginning of this section of notes, a 1 to 10 ratio is the same as a 2 to 20 ratio. So I think fractions are fine. I would stick with the fraction. All right. But if you don't like fraction, just multiply everything by 2 and that takes care of it. So those are combustion reactions. Those are some of my favorites. I think they're just nice and easy. There are a couple more equation types we need to know. The alkali metals, right? Sodium, potassium, lithium, cesium. There's a couple of reactions we can do with these. One of them, their combination, they combine with either a halogen like chlorine, bromine, iodine, or oxygen. So the thing we have to remember, and we just saw this too with the O2, is that when we do equation writing, there are 7 diatomic elements. And when we talked about this, I said, well, we don't really need it until we get to equation writing, and then here we are. When I was memorizing these, I thought, oh, it looks like a 7 on the periodic table, right? Hydrogen's kind of off on its own, but then it goes NOF, ClBr. Another way to do it is to remember Hofbrinkel, and this was what was in the notes. Those are your 7: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, or the 7 on the table. But these 7 elements in their elemental form, not as ions, but in their elemental form, they are diatomic. So oxygen, gas, O2, chlorine, Cl2, fluorine, F2, nitrogen gas, N2. So if I'm going to take an alkali metal like sodium and combine it with a halogen, they're going to combine and form an ionic compound, metal and nonmetal. Then I think about charges on the product side, right? Alkali metal +1, halogen -1. These should be a 1-to-1 ratio. But because chlorine is a diatomic, right, it has to appear as Cl2. I'm going to put a 2 in front of NaCl to balance the chlorine. but that means I just need to also put a 2 in front of Na. Now, the other one here would be oxygen. That's another possibility. So let's practice that. If I put potassium, metal, and I react it with oxygen, all right, note here, it's metal potassium, solid. That means it's not the ion, it is the neutral metal, no charge. The oxygen gas, same thing, no charge. It's neutral, it's not the ion. If it were the ion, this would say oxide. If it were the ion, it would say it was potassium ion, but it's not. It's elemental, solid potassium, no charge, reacting with oxygen gas, O2. Now, when they come together, they're going to form an ionic compound. Now, potassium is +1, oxygen's -2, because now we have formed ions, because it's metal and nonmetal. So I'd have to have 2 potassiums to balance out the charge on the oxygen. Now, there's 2 oxygens on the reactant side because it's diatomic, O2. So I need to put a 2 in front of K2O on the product side to balance the 2 oxygens. That gives me a total of 4 potassiums, so I'm going to put a 4 in front of the K. Now, combination reactions, these are different from double displacement. Double displacement, we were always looking at ions in the compound, but what we have here is we have single substances, not compounds. So separately, no charge. Together, now they have their charges. All right, same thing, but now we look at what's called single displacement reactions, where you have a single metal, again, by itself, neutral, no charge. And what'll happen in single displacement is you react it with a cation in ionic compound or hydrogen, in this case, in an acid or water. And if they switch places, all right, which we talk about more in a little bit, the sodium kicks off the hydrogen and the hydrogen comes out to be the neutral. So really in the water, we have H with OH. So you have your neutral metal reacting with an ionic compound. In this case, hydrogen is the cation, hydroxide is the anion. If they switch places, the sodium then would become the cation and the hydrogen would become the neutral. All right, so in a single displacement, that's what happens. Neutral becomes the cation becomes the neutral. Now, hydrogen, again, part of Hofbrinkel, so that's why it's showing up as a diatomic as H2. Now, with single displacement reactions, we're going to need a little more information, but we're not quite there yet. It's going to be the activity series of metals, if you remember seeing that. But they actually talk about this more in chapter 5. So we're not too worried about predicting this just yet. If you notice with the water, it'll give a statement. It'll say, okay, the alkali metals combine with water to form the metal hydroxide. There's the metal hydroxide and hydrogen gas, H2. All right, so that's single displacement of a alkali metal with water. So again, Tro does things in a slightly strange fashion, I think, the way he organizes it in the book. Whereas the equations that we're looking at in chapter 4, we've got combustion, and then we have reactions specifically with alkali metals. Alkali metals, sodium, lithium, potassium, how they combine with either halogens like chlorine, oxygen, or with water. Those are the 3 things that we're looking at, but it's always just alkali metals with one of those 3. Okay, so those are the 3 possibilities. All right, so we're going to look at some examples on the next page. Okay, so 2 questions to go to review. Like the chapter kind of stops there, but I felt like we needed a little bit more. So we've got potassium metal combines with oxygen gas to form potassium oxide. Let's do the equation first. Okay, so potassium metal, meaning it's neutral, combines with oxygen, O2 has to be because it's part of Hofbrinkel, and it forms potassium oxide, ionic compound, K2O. So this is the one we just did a little bit ago. So to balance 2 oxygens on the product side, we need 2 oxygens. So we put a 2 in front of K2O. 2 times 2 means we have a total of 4 potassiums. All right, so this is our balanced equation. All right, so one of the 3 possibilities, alkali metal with oxygen, this is one of the three, all right? So if you swap lithium, sodium, cesium, it looks exactly the same. You just swap out the K for Li. But otherwise, this is the equation of the alkali metal with oxygen. Question says, what would be the percent yield if 82.5 grams of potassium oxide was formed from reacting 75 grams of potassium with 75 grams of oxygen? All right, so I'm going to do this what I think is the simpler way. I'm going to go A1, convert to B, and I'm going to go A2, convert to B, find my theoretical yield, then do percent. Now, as we were talking about, these questions in terms of stoichiometry, these are some of the hardest ones because I've got 1, 2, 3 numbers given. But remember, if you're asked for percent yield, actual yield has to be given. The actual yield will be a yield, right? It will always be for the product. So that means this K2O product, 82.5 grams, that is the actual yield. So the reason why I like doing that is because it says, okay, let me take out the 82.5. I'm going to save that for later. And it also tells me that my first job is going to be to figure out what the theoretical yield should have been. And that's how I know it's my B, right? And it's a yield question. So I know the product is always my B. Okay, so A1, go to B. I have 75 grams of potassium. Molar mass based on 1 mole of K. Remember, we're not looking at the 4, we're just looking at the K, is 39.10 grams based on the periodic table. Now I look at my mole to mole ratio, getting rid of K on the bottom, going to K2O on top. This is where the coefficients come in. So now I look at the 4 and the 2. So on the bottom with potassium, 4, and on the top with K2O, 2. Last one here for 1 mole of K2O, 39.1 times 2 added to 16. I get 94.20 grams. All right. Sorry, that looks like a Q. It's a 9. 94.20. Working backwards, times 2 divided by 4 divided by 39.1 and then times 75. So just multiplying everything through, I get 90.3 grams of K2O, all right, which may or may not be my answer, right? Now I got to do A2 to B. So I start with my 75 grams of O2. 1 mole of O2. Oxygen is 16, taken twice would be 32 grams. All right, then my mole to mole ratio, for every 2 moles of K2O, I only need 1 mole of O2. And then that molar mass, again, same for both setups. 94.20 grams is the molar mass of K2O. So on my calculator, 75 divided by 32 times 2 times 94.2. And here I get 442 grams of K2O. All right, so you can see that when you're given the quantities of the 2 reactants, you cannot tell which one's limiting until you start doing some work. The molar masses are slightly different, but the big difference is you need 4 times the moles of potassium as you do oxygen. So that's why potassium is the limiting reactant, and the 90.3 grams of K2O would be the most amount you could make. All right, question was, will the percent yield always be greater than the 2 substances? Oh, the actual yield. Not necessarily. No, the actual yield, it doesn't have to be more. It can depend because you could have more than one product. And if you imagine like a lot of the mass that's in the reaction could be going towards that second product. So the actual yield, you can't know going in that it's always going to be greater. The actual yield, though, it will always be given. That's a good part. So your actual yield in this question was given as 82.5 grams. Ooh, I misspelled that, of potassium oxide. Now our theoretical yield, we just found out, in theory, right, would be 90.3 grams because we found out the potassium was our limiting reactant. Oxygen here would have been excess. So now at this point, I can find my percent yield. So percent yield, actual 82.5 grams, theoretical 90.3 grams, keeping our three significant figures. We get a 91.4% yield. Okay, so that would be the percent yield of this question. All right. So if you've got a percent yield question, remember it will always be for the product. So we know the percent yield is always going to be for whatever's on the product side, which means that number given was the actual yield for K2O. So starting with the other two reactants, convert them both to that product, figure out theoretically how much you could make, circle the smaller, because that means that that reactant was the limiting reactant. That is your theoretical yield. In theory, that's what we should have gotten. But now let's compare it to what we actually got. So actual over theoretical times 100. All right, one more question to look at. It says, what mass of CO2 would be made from the combustion of 15 gallons of octane, which has a density of 0.703 grams per milliliter. And we're given a conversion factor there, which is actually one of the ones that you need to memorize from chapter 1, but just in case it's been a while. All right, so this one really actually is one of the 6 that you have to memorize. Okay, so first thing is, I noticed that I am comparing octane and CO2. So the first thing I need is the balanced equation. So I've got a combustion reaction. So we looked at those. You take your C8H18. It's a liquid because we're talking about gallons. We need oxygen from the air to convert all of the carbon into carbon dioxide and all of the hydrogen into steam. All right, now, next part, we talked about whatever that subscript is for the carbon becomes the coefficient for the CO2. So 8 carbons means we need 8 CO2s on the product side. The hydrogen, we had a subscript of 18. The multiple of 2 that gets me to 18 would be a 9. So we put a 9 in front of water. When I go to calculate my oxygen now, I've got 8 times 2, which is 16. And then another 9 in the water. So I have 25 oxygens. So on the product side, to get me to 25, you can either put 12.5 in front of O2, or you can put 25 divided by 2. All right, and again, I think fractions are fine, so we're gonna leave it there. So we have 15 gallons of octane, and we wanna know the mass of CO2. Okay, so we had talked about conversion factors, and I kind of like getting those up front. If we're looking for mass, we know that we need molar mass. 1 carbon and 2 oxygens from the periodic table is 44.01. Now the octane, we haven't really talked about this. We have a liquid and we have a volume. We have gallons. We have gallons. And we are sort of seeing here that we're probably going to go to liters first. All right, then liters, we could go to milliliters. And we also have a density. So we're going to use the density to get mass, right? Because we'll be able to convert between milliliters to grams. And then once we have mass, we're going to need molar mass to get to moles. So if I take those 8 carbons at 12.01 apiece and add that to the 18 hydrogens at 1.01 apiece, we get 114.26 grams. So we have our octane going to our CO2. No mention of oxygen here. So we're just assuming oxygen is excess. This is not a limiting reactant problem. So we just have to go from octane to CO2. So we have 15 gallons of C8H18. 1 gallon on the bottom is 3.785 liters. 1 liter is 1,000 milliliters, or if you want 1 milliliter is 10 to the negative third liters. Density, 0.703 grams per milliliter. So we're just basically at this point doing chapter 1 unit conversions. Okay, so that was everything we did in chapter 1. Now what we're going to do is bring it into chapter 3 and 4, which is we're going to now go to moles. So periodic table told me 114.26 grams is the mass of 1 mole of C8H18. Now the chapter 4 piece, let's do the mole to mole ratio. 1 mole of C8H18 makes 8 moles of CO2, right? And that's why if you multiplied everything through by 2, your ratio is still the same. Instead of 1 to 8, it would be 2 to 16, but mathematically it'd be the same. And then to get to mass of CO2, 44.01 grams is the molar mass of 1 CO2. Sorry for like running out of room there. Okay, so 15 times 3.785 times 1,000 times 0.703 divided by 114.26 times 8 times 44.01. Okay, get a large number. Calculator, 122,987 grams of CO2. If we're thinking only 2 significant figures, we'd go 120,000 grams of CO2. Okay, so, that's a lot of mass of CO2 from 1 tank of gas, but that's how you would find it out. So we had our gallons unit, we convert to liters, and then milliliters, just unit conversions, bringing in density to take us to mass. Then from here, this is our chapter 4. Mass of A to mass of B. Molar mass is the conversion to get to moles. Mole ratio goes in the middle. Ratio, of course, comes from the balanced chemical equation. All right. So those last 2 questions there were kind of a review. This last question, I wanted to do another combustion reaction. I know it's the same one that's in the notes, but then also look at how do we bring in volume? So if I could make you a flow chart of what we have so far, like all the pieces put together, what we learned in this chapter, which is sort of the center point of all stoichiometry, is that if we're going to relate 2 substances in a chemical equation, the only way to do that is through the mole to mole ratio. When we learned our equation, we're going to do more of this in the next chapter after the first test. But when we look at chemical equations, we have 4 substance types: solid, liquid, gas, aqueous. So if you had a liquid, you're probably going to take the volume of that, like the 15 gallons of octane. So what you're going to do first is convert that to mass using density, and then mass would go to moles using the molar mass from the periodic table. All right, so that conversion of volume to mass, that is the density. So D for density. I'll just write it out. All right, then if we have the mass of a solid, right, it's more straightforward. We just use molar mass to get to moles. Then the other conversion that I said we used in the beginning, but we probably won't very much after this, is if we had particles of A, we go to moles using Avogadro's. Then the right side looks just like the left, right? It's a mirror image. That once I get to moles of B, if I want mass of B, I use molar mass from the periodic table. If I want particles of B, like atoms or molecules, that's when I use Avogadro's number. All right, so this is all the pieces we have so far. So volume to mass, like we did here, that was chapter 1. Mass to moles and particles to moles, that was chapter 3. Converting A to B, mole ratio, that's chapter 4. And again, that comes from the balanced chemical equation. So that's everything we've got so far. We're going to keep adding to this, but in terms of getting started with stoichiometry, this is everything we have so far. All right, so that's the end of chapter 4. The first 4 chapters are on the test. Test is coming up Thursday next week. So if you haven't started those dynamic study guides, please do so. It's a lot of extra credit. I do not want you to miss out on the extra credit. So you have everything you need to start studying for the test. Chapter 4, remember, whatever chapter is the last chapter we cover before the test, there will not be a credit quiz. There will, however, there will be practice quizzes there for you to practice, as well as the dynamic study guide and the homework in the Tro book. But there's no credit quiz for chapter 4. I want instead you to focus more on studying for the test than for the credit quiz. So there's a lot coming up. Let me just kind of break it down for you because summer is just, it's really quick. All right. So chapter 1 is done, right? We've already got that done. For chapter 2, that credit quiz is due tomorrow, Friday at 11:59 p.m. So that's due tomorrow. Chapter 3, which we finished on Tuesday, that credit quiz is due Monday at 11:59 p.m. Chapter 4, right? Again, no credit quiz, just practice quizzes. And practice quizzes are due sorry, they're not due. They're open the whole semester. So they're not due. They're open the whole time. You can do them whenever, but I definitely encourage you to do the practice quizzes before taking the quiz or the test, just because I think they help you with the material. So then what's coming up is Tuesday next week, we're going to review. If you go into my courses, there is a folder for exam reviews. So it's going to be the same thing. You can print that out ahead of time if you want. And then Thursday, exam 1 is going to be open from 12 a.m. until midnight. So you have all day Thursday to take it. It is proctored with Respondus. If you have not used Respondus before, it's an AI proctor. There is a practice test. It's not a practice chemistry test. It's just a practice Respondus test. So if you want to go through the motions of signing on to Respondus and knowing how it all works, there's a practice test for you to do that. So you can make sure your system is good to go. I would do that because I'd always be paranoid that something would go wrong and I'd find out like right when I'm supposed to take the test that I don't have what I need to have. All right. So because our exam is Thursday, that means that on Wednesday, your dynamic study guides, the extra credit, are due. So all the due dates are at 11:59 p.m. So this is how everything is looking in the next week. All right. So Thursday, there will not be lecture. Tuesday, we're going to do the review. Thursday, we're not going to have class because like if we were meeting face to face, you would be using that class time to take the test. So you're going to be using that time to take the test. You won't see me on Thursday. Unless you have questions for me or something, right? We can always do a Zoom session, but I'm not planning one. But if you request one, that's totally fine. So Tuesday we'll review. Wednesday, you'll make sure your extra credit is due. Please don't miss out on those points. It is 25 points out of 200. So it's like an entire letter grade bump to do those dynamic study guides. So please do those. And again, that's at the Pearson site. So if you need to find those, let me know. And then Thursday will be the test. All right. And then I think there was one more question that came in the chat box kind of hit it for me. Will the percent yield always? Nope, that was the question I already did. Let me go back down. Oh, is exam 1 similar format to the credit quizzes? Exam 1, the format will be similar. So some of the questions are going to be multiple choice, like nomenclature is probably pretty easy to do multiple choice. But as you can imagine, I had like, I think it was about 2 years ago now, I had students that were cheating. And unfortunately, I have to do my best. Well, that's not the unfortunate part, but the only way I can really work around the plugins is if I make you show your work. So there's going to be questions there where you have to type in your work. You have to show your work. I know that takes longer. You have, I think, a pretty good amount of time on the exam. So there will be a mix. It'll be a mix of multiple choice, some fill in the blank, and then some short answer, show your work questions. So very similar to the credit quiz. There's going to be some things you type in, some things you just pick. All right. And then how many questions? Somebody always asks me that and I always forget to look. So sorry, I'm going to write myself a note. And when we do the review on Tuesday, I'm going to tell you exactly how many questions are on the test. All right. So that'll be a deal for Tuesday. I'll have that review ready to go. You would think after 20 years of teaching, I would always know the answer to that question because somebody always asks, but yet I somehow always forget. Anyway, I hope you all have a great weekend and great rest of your day. If you have any questions for me, let me know. I'll be around this weekend if you need to do a Zoom session, but if not, I'll see you back Tuesday. All right. Have a great day.